expressing the distribution of the sum of two independent random variables in the convolution form is important because you see the convolution in the frequency domain or the omega domain or the S domain or the Z domain, all domains which we have discussed when we discussed transform functions like characteristic function, generating function, Laplace transform, etc., uh, has a special property where we call this the convolution property. It's valid for Fourier transform in general, but it also applies to Laplace transform, Z transform, etc. Therefore, any sort of generating function or transform function you have, you can make use of this convolution property. So what is this convolution property? Essentially, remember the characteristic function of the distribution of x, well, it is defined through this expectation, if you remember, is essentially the Fourier transform of the PDF evaluated at minus x. And as we have seen, uh, when z is equal to x plus y and x and y are independent, we have seen that the PDF of z turns out to be equal to the convolution of the marginal PDFs of x and y due to the independence, okay? Remember, this is important. This is valid only for independent x and y, not in general, okay? Only for independent x and y, okay? Now, the convolution property says that convolution in time domain or in x domain, in our case, is equivalent to multiplication in frequency domain. So frequency domain in this context means either the omega domain or the z domain or the s domain when you talk about Laplace transform, okay? So what does that mean? When the PDFs of x and y are convolved, that is equivalent to this expression. The characteristic function of z, which is x plus y, equals the product of the characteristic functions of x and y, okay? This is why this makes our life so much easier. If you know the characteristic function or a similar transform of these random variables x and y, which are independent, then you can obtain the characteristic function of their sum very easily. Just multiply them, you get the characteristic function of their sum. You can also observe this from the definition of the characteristic function, because you see it's defined as the expected value of e to the power j omega z, the characteristic function of z. And instead of z, just write x plus y, and then separate these terms, e to the power j omega x, e to the power j omega y. Now, this is a function of x. This is a function of y. Well, obviously, if x and y are not independent, you can't do anything here. This is a joint distribution. You have to know the joint distribution to obtain this joint characteristic function. But if you know that x and y are independent, then you can separate these two, because this random variable, e to the power j omega x, and this random variable, e to the power j omega y, will also be independent. Therefore, I can write this as the product of their expectations, which are by definition the product of their characteristic functions. But you see, independence is essential here, because otherwise I cannot separate these two, okay? Very important. This is valid only for xy independent. Never forget this, okay? And another point I would like to emphasize again, generating function, Laplace transform, characteristic function, moment generating function, this property works with all of them as long as the distribution is suitable. For instance, if you have a discrete distribution defined on the set of natural numbers, you can make use of generating functions in this context. Or if you have a continuous distribution which is non-negative, you can use this using Laplace transform of the PDF, and so on. Okay, so I will give you examples now. Here, again, the same discrete distribution, the joint distribution. And remember, we have observed that x1 and x2 in this distribution were independent. which is essential. And let's obtain the distribution of x1 plus x2, which we define as random variable y. Now, in this case, of course, this is a simple joint distribution, and you can obtain the distribution of y quite easily by just looking at this joint distribution. But you see, from the marginal distribution of x1, you can write the generating function as 0.4 times z to the power 0, because you have 0.4 probability for z equals for x1 equals 0, and x1 equals 1 has the probability of 0.3. Okay, 0.3 times z to the power 1 plus 0.3 times z to the power 4, because x1 equals 4 has again 0.3 probability. Okay, similarly, the generating function of x2 is 0.4 times z to the power 2, because at 2 you have 0.4 probability for x2, and at 5 x2 has probability 0.6, so this is 0.6 times z to the power 5. These are the generating functions. Multiply them. Since x1 and x2 are independent, the product of these two generating functions will give me the generating function of their sum. Okay, multiply them term by term, you obtain this generating function. And by looking at this, you immediately see the distribution. At 2, you have 0.16 probability. At 3, you have 0.12 probability. At 5, you have 0.24. At 6, you have 0.3 probability. At 9, you have 0.18 probability. Okay, you can see this also from the joint distribution. For instance, at 4 and 5, the sum is 9, and the probability for that is 0.18. Okay, for instance, you have 1, 5 with probability 0.18, and 4, 2 with probability 0.12. These two pairs give you the sum of 6. Okay, and together you have 0.18, 0.12. You have a total of 0.3 probability, which appears here. Okay, so generative functions also lead to the generating function of the sum of the independent random variables.